Hello, Mr. Betts here. I want to take a look at a particular implicit relation. This is actually the graph that I used in the introduction video and actually do some of the stuff that I talked about. So the first part here, we just want to find the derivative dy dx. So this really goes back to a Unit 3 topic where we're using implicit differentiation, but let's go through that here. So we're going to take the derivative of everything with respect to x. So keep in mind when we take the derivative of y's, we're going to be multiplying by dy dx. Now in this particular example, we are going to be using the product rule on both of these terms here. So just getting going here, derivative of x is 1 times y squared is y squared, plus the first times the derivative of the second, and then derivative of the first times the second plus the first times the derivative of the second, and then the derivative of 8 is just going to be 0. And then we want to get dy dx by itself, so anything that doesn't have dy dx in it, we're going to move to the other side. So I'm going to have dy dx, and I'm going to factor out dy dx from the two terms that we're going to leave on the left side here. So we're going to have 2xy minus x cubed equals, and then moving the other terms to the other side, we're going to have 3x squared y minus y squared. And then we divide both sides by 2xy minus x cubed. So we get dy dx is equal to 3x squared y minus y squared over 2xy minus x cubed. So this is a skill that we should already have, but now that we have that derivative, we can use that derivative to analyze things going on with the graph of this implicit relation. So we can use this to find things like where we have a horizontal tangent, or where we have a vertical tangent, or where the function is concave up or concave down. So we're going to answer a couple of these questions here. So we will often see problems where we're given an implicit relation and the derivative. Usually this happens because we want to answer questions using the derivative, and we want to make sure that we don't make a mistake finding the derivative and then we aren't able to answer the questions accurately. So this is a pretty common thing to see on the AP test, where they'll give us a relation, say, here's the derivative, but show that that's the derivative. So we would do what we did here. And then use that derivative to do things beyond. So in this part, we want to find the x-coordinate where the curve has a horizontal tangent. Just looking at the graph here, it looks like we're going to be looking for the x-coordinate of that point right there. So a horizontal tangent means that the slope of the tangent line is going to equal 0. So we want to know where dy dx is equal to 0. So I'm going to find that by setting dy dx equal to 0. But dy dx is going to be equal to 0 when the numerator is equal to 0. So I'm going to simplify this right off the bat and just set the numerator equal to 0. So 3x squared y minus y squared is equal to 0. And then I want to solve. The problem that we have here is we have a single equation that has x's and y's in it, and we want to solve for, well, particularly the x-coordinate, but we need to solve this equation. And we can't do it exactly. We can get closer, so we can factor out a y. And if we do that, we get 3x squared minus y is equal to 0. So that actually does give us one solution. So one solution is going to be when y is equal to 0. However, if we plug that into our equation here, we get 0 is equal to 8. Weird 8. Let me try that again. And that's not going to be a true equation, so that's not a point on the curve. And if you notice that y equals 0 in our graph here, the function, I shouldn't say function, the relation is never actually going to have y equal to 0. Y equals 0 is an asymptote, but it's not going to be a point, or not going to give us a point on that relation. So y equals 0 is not on the graph. What that means is the 3x squared minus y has to equal 0. But we can't solve that for x or for y because one depends on the other. So I can I can solve for y and get 3x squared. However, y equals 3x squared is a parabola in this coordinate plane that's going to look something like this. And so it gives me a bunch of points that are not even on the relation, and I want the x coordinate of that specific point. So what we have to keep in mind is the point that we use as an answer to this equation also has to satisfy this equation because it has to be on the graph. So what I'm going to do is I'm going to take this expression right here and plug it in for y here so that we can solve for x. So rewriting this, x times y squared, replacing the y with 3x squared, minus x cubed times y equals 8. Now I can use this to solve for x. So I have an equation with only x's in it. So we're going to have, looks like 9x to the 5th minus 3x to the 5th equals 8. So 6x to the 5th equals 8. X to the 5th equals 4/3, and then the 5th root. And this is it. This is all we're looking for here. I do want to point out that we can use this and plug it in here to get the y coordinate also. That's just, it's messy. It ends up being 3 times the 5th root of 16/9 for the y coordinate. So if it is messy, a lot of times you won't be asked to find more information. We could, and I'm not asking to do this, but we could take this another step, take the second derivative, plug the x and the y coordinate into the second derivative to determine that it's concave up at this point, and then say that that's going to be a relative minimum. So not only find the coordinates of the horizontal tangent, but determine if it's concave up or concave down at that horizontal tangent for a relative extreme. That would be using the second derivative test. What we do want to know here, though, is another one. Instead of a horizontal tangent, we want to know where the graph has a vertical tangent. So looking at the graph here, we can see that it's going to have a vertical tangent somewhere around here. And this time we want to find the coordinates, meaning x and y. So with a horizontal tangent, remember the derivative equals 0. A vertical tangent, the derivative is going to be undefined. Now, in particular, the derivative is going to be undefined because it's infinite, and the derivative is going to be infinite where the denominator equals 0. So where we set the numerator equal to 0 for a horizontal tangent, we're going to set the denominator equal to 0 for a vertical tangent. We can, this is pretty similar to the horizontal tangent. We can factor out an x. So we get one solution where x equals 0. But if we plug 0 in for x up here, we get 0 equals 8 again. So again, x equals 0, which is the y-axis, is not a solution on this relation, so it's not on the graph. But the other factor here, 2y minus x squared equals 0, gives us a relation that is going to give us a solution. I'm going to solve this for y. So y equals x squared over 2. And just like I did with a horizontal tangent, the solution, the point that I'm looking for here, is going to be a solution to this equation and this equation. So I'm going to plug the x squared over 2 in for y. And simplify. Get x to the 5th over 4 minus x to the 5th over 2 equals 8. I'm going to get rid of fractions by multiplying by 4. And so we get negative x to the 5th. I forgot to multiply by 4. Negative x to the 5th equals 32, or x to the 5th equals negative 32, and x is going to equal negative 2. Now, since this is kind of a cleaner answer that we got with our horizontal tangent, that's why I asked for the coordinates. So let's find the y coordinate also. And we can plug this solution into this equation, or we can plug it into this equation. Either one works, but this one's a lot easier. So usually at some point along the process, we're going to have an equation where it's y equals something in terms of x. So we're going to get y equals negative 2 squared over 2, which is 2. And so the answer to this then is going to be the xy coordinate, which is negative 2 comma 2. And indeed, if you look at the graph, it looks like, I know that it's not scaled here, but it looks like negative 2, 2 seems a plausible answer for the coordinates of this point where we have a vertical tangent.